Hello everyone, welcome to the Physics 2 lab. Today we are going to talk about RLC circuits lab and resonance frequency. So here R stands for resistance, L stands for inductance, and capacitor or DC refers to capacitance. So here we are talking about a circuit that contains these three elements. Okay, so we are talking about a circuit like this one. It has a resistance R, it has capacitance C, and it has also an inductor, which is L. Okay, and this is basically all of it's connected to a power supply, a variable or AC power supply, and let's say it's a sine wave power supply here, V of T, let's say power supply. So this is RLC circuit that's connected to an AC source. So here there are some points that we would like to talk about first. First, if you have a sine wave, let's say it starts here from 0, let's go up, down, down. So basically the amplitude of this sine wave, let's say it's 2, so it has amplitude of 2, okay, and minus 2. So the voltage, or like the value peak to peak, it is 4, okay. Then basically this one could be over time, and we say that this sine wave repeats itself at this point here. If you see the cycle sine wave, that starts to repeat itself again after that, and usually we say this one as a sine omega t, which is also equal to sine 2 pi f t time. Okay, so this signal repeats itself every period, and this duration we call it the time period of the sine wave, time period, and the time period basically is equal to 1 over f, which is the frequency. So the time period is equal to 1 over f, which is the frequency of this sine wave. Okay, and we also have the omega. Omega, it's basically the angular frequency. Okay, the angular frequency, 2 pi f. And usually this omega, it's measured in degrees, okay, or a radian in this case. So we have one period of this cycle, it has a time of t, and basically we can get the frequency of the sine wave, and also this period of one cycle, it's basically represented as a 2 pi, okay, in terms of radian. We have the omega, the angular frequency, which is equal to 2 pi f, and we can see this is sine, and basically usually sine has what? Has a theta, some angle inside, sine angle, and the angle in general, any theta could take a value from 0 to 360. So this representation could be also from 0 to 2 pi. And basically, after 360 or 2 pi, which is basically the signal, is going to repeat itself again. It will start from the beginning. When you have a circle with some angle here that you go up, theta here is going to be 0 until this angle becomes again 360 at this location. Almost here, and this one is going to be 0 value. So 0 goes up 1, 2, 3, 4 until it becomes 360, then start again to repeat itself. It's a cycle, the sine wave. So you could either represent the theta in terms of 0 to 360 or the 0 to 2 pi. Okay? So we can see the sine wave. It goes from 0 to 2 pi. So this is 0. This also we can consider it as a 1 cycle, which is 2 pi. And this means that this middle point is a pi. And basically this peak, it is an pi over 2. And this peak, it is 3 pi over 2. Which basically, pi over 2 represents the 90 degrees. And this one represents the 180 degrees. This one 270. And this one basically 360 degrees. Okay? So we wanted to understand first what is sine wave. It has an angle inside. This angle, or this, theta inside is equal to omega t, because it's a function of time. Omega is equal to pi f. Omega is the angular frequency, is equal to 2 pi f, and f is the frequency of the sine wave, and t capital is the time period of one cycle inside this sine wave. Okay? I hope you get this concept first. So after talking about this concept, let's understand what happens inside the capacitor. So if you have a capacitor here, and you apply some sine wave on it, basically what happens is that the capacitor itself, it's as electrical storage element. So the current here goes inside and starts to fill this capacitor with the charges until it becomes fully stored, or full of energy, or full of charges. So at this point, the current goes first to charge or to fill this capacitor with energy, and the voltage starts to come up or to start to increase until it becomes the maximum voltage as the power supply. So at this condition, because it comes first, we say that the current of the capacitor leads the voltage of the capacitor by 90 degrees. Okay? How is this? Basically, if you assume that this is the volt of the source itself, which is, in this case is going to be, because it's in parallel with this capacitor, so it's going to equal to the voltage of the capacitor. So if we were to draw this time domain, let's say with the black color, we're going to say the IC, the current itself. So if we started, the current is coming from here, going down, up, down, up. And we said that this is, let's represent this one as the angle itself, theta. So we know that this is going to be 0 angle. Let's say this one is going to be 90. And this one is going to be 180. And this one 270. And this one is 360 to have a complete cycle, which also is equal to pi over 2, pi, 3 pi over 2, and this one is 2 pi. So if the current starting from here at 0, it was the maximum, so the voltage basically comes after. So the current comes first, then the voltage comes after with the 90 degrees. So that means at 90 degrees, we are going to have the voltage itself. So the voltage starts here and start basically to come So the current comes first, then the voltage VC comes next after 90 degrees. Okay? So this is the case of the capacitor itself. So let's see the case of the inductor. So the inductor is also a storage element that stores magnetic energy. We have this one, is L, and also you have here the Vs T, and you have some current I. So what happens here, when you apply some voltage on the inductor, there's some current is going to be produced. But as you know, that the coil itself, when the current starts to go through it, is going to create or generate some magnetic field. Current going inside a metal or a coil, or a wire, start to generate magnetic field. And using the Faraday's law and Lenz's law, when the current starts to increase inside, the coil itself is going to magnetic field that creates a voltage that opposing the increase of the current itself. So what does that mean? That this coil resists the increase or the rise of the current inside the coil, so that it takes time for the current to go up, which means that the voltage in this case is going to volt, which is here, is going to also equal to the VL. Leads comes first before the current itself inside the coil by 90 degrees. So you can see that here for the capacitor, the current comes first, then the voltage. However, for the inductor, the voltage comes first, then the current itself inside the coil. So I hope you got these two parts. And inside the circuit, if you have AC, the capacitor itself, we call it capacitive reactance. Capacitive reactance. And we call it XC, which it's something like a representation of a resistance, XC. And this XC is equal to basically 1 over J omega C. And the inductor, or this inductor, we call it an inductive reactance. And we call it XL. And this one is going to equal to J omega L, which is omega is the angular frequency, which is equal to 2 pi F. Okay? So the capacitor becomes capacitive reactance. And this basically the unit for this one is going to be ohms, the ohm. And this one, the inductor becomes inductive reactance, and the unit is going to be also ohms. Okay? I hope you differentiate between these two. In case of a resistance, which does not store any energy inside, so usually the VR and IR, the current and the resistance, are in phase. Which means the voltage and the current, both of them comes at the same time. So in this case, if you draw the current and voltage here, so if you have the current, it's going to be like this, and the voltage, VR, and IR and VR. So the voltage also is going to be the same, maybe different values, but the same. They are in phase. There is no phase difference. So here, if you get to put a point at the peak here and the point at the peak here, the distance or the difference here, delta theta, is equal to 90 degrees. Okay? I hope you understand the difference between the capacitance behavior, the inductor, and the resistance. Okay? So let's go to combine all of these in one system, which is the RLC circuit. So now for the RLC circuit, you have resistance, capacitor, inductance. You have here the power supply. We have here R, C, L, which basically for the C becomes capacitive reluctance, C, and this one we have it's XL. So these are the ones. So we have the voltage, the power supply S itself, so Vs. So usually these three parts are resistors, okay? But inductive one and capacitive one. So the whole, we can call it as an impedance, Z. Impedance. And the value of the impedance in this case is equal to basically the root square of R squared plus XL minus XC square. Okay? Basically, if you know more advanced, this is the real part, and this was imaginary. That's why we got the resultant of these two values, R squared plus XL minus XC total square. And this negative value, because basically they have 180 degrees in phase difference. They have 180 degrees phase difference between the L and C. For example, the voltage. The voltage here, the phase difference between the voltage on the inductor and the voltage on the capacitor is going to be 180 degrees. Okay? I hope you got this one. So in this case, basically we can say that the voltage is equal to impedance, which is the Vs. The voltage of the power supply is equal to the Z, the impedance, multiplied by the current, the total current in the system itself, I. So here, from this curve, we can see that the resistance here is constant, and the XL is equal to J omega L, and the XC is equal to 1 over J omega C. So usually we can see that the L is going to be constant usually, the capacitance is constant, so we have only omega. Omega is equal to 2 pi F, the frequency. Frequency of what? Frequency of the power supply. So we can see that inductive reactance, if we change it the F, the power supply frequency, the value of the inductive reactance changes, as well as the value of the inductive capacitance is going to, the capacitive reactance is going to change. So the omega, or the frequency of the power source, when we change it, these values, two values, are going to change. So from this equation, we can see that R is always the same, but here we have a subtraction process, which means that this could be equal to 0 in some way. Okay, so when the XL, the inductive reactance, equals to the capacitive reactance, at this point we are going to have this Z is going to be minimum. The impedance is minimum. And when the impedance is minimum, that means what? It means we are going to have I max. The maximum current is going to go inside the circuit itself. And this is the condition that we call a resonance. Okay? What frequency is going to make this condition, which basically XL is equal to XC, so that we have the minimum impedance, which lead to the maximum current inside the circuit. So basically, to do this one, it's simple. We can do that. Omega L is equal to 1 over omega C, which basically it says that 2 pi F squared is equal to 1 over LC. Okay, so that means F resonance is equal to 1 over 2 pi the square root of L inductance multiplied by the capacitance. Okay, so this is how we get the resonance. And basically, at this point, I maximum, that means we have also that the voltage and the current are in phase. They don't have any phase difference between the two signals. And in this condition, so here at resonance, XL is equal to XC, Z is going to equal to R, the resistance value, and the voltage is equal to R multiplied by I, and in this case we are going to have I is going to be maximum, and this is going to be the minimum value, the impedance itself, and the relationship here becomes linear. Basically, if you were to draw I with the voltage, you can see it's going to be a straight line here, which represents the resistance itself, which is the slope. It's going to be the slope of this line itself. Okay? However, at any different frequency other than the resonance frequency, you are going to have an impedance, you are going to have a phase difference between the current and the voltage, and the relationship in this case is going to be something like an ellipse shape, which means that at different values, this ellipse shape, it changes, okay, based on the frequency value. Might be get bigger, it might get smaller. And we are going to see all of this during the lab for today. So let's go to the lab.
Resistance slows the flow, it's heat you'll see. Inductance stores magnetic energy.